Alright, now we're going to do some oxidation numbers. Remember that oxidation number is for covalent compounds, and it is similar to ionic charges. Not exactly the same, but similar. So we have bromine attached to 3 oxygens with a -1 charge. When it's an anion, it has to add up to the -1 charge. Oxygens are always a -2, so we have a -6. So what? -6 gives us -1, a +5. Oh, that's not going to work. There we go. HSO4, same story here. You know hydrogen's going to be a +1. It's got to add up to -1. Our oxygens are going to add up to -8. So what does the sulfur have to be? What? 1 plus what? -8 gives us a -1. That would be a 6. Finally, this is a weird one. Uranium monoxide. Uranium, it's got a 2+ charge. Oxygen's almost always -2, so we've got to have a +4 here. Number 30, determine the oxidation number once again. NH3, adds up to 0. Hydrogens are going to be a +1 when they are with nonmetals. So nitrogen here has to be a -3. -3 +1. Okay, sulfite. So 3, -2, +4. 4 minus 6 is -2. All right, what's being oxidized? Carbon here. C4H8. If the hydrogens are a +1, each carbon's got to be a -2. Oxygen in the second part is going to be a 0 oxidation number. Carbon dioxide, that carbon's going to be a +4. Hydrogen's a +1. The oxygens are -2. So the oxygen is going from a 0 to a -2. So it is being reduced. Its charge is going down. It's gaining electrons. So we'll move oxygen up here. That means the carbon is what's being oxidized. The oxidizing agent is what is being reduced, so that's going to be oxygen. And the reducing agent is what's being oxidized. There you go. Down here we've got tin. Tin's going to be 0 because he's an element. Chlorine is going to be 0 because he's an element. Tin 4 chloride. The tin charge went up, so the tin is oxidized. The chlorine is reduced. Therefore, the chlorine is the oxidizing agent, and the tin is the reducing agent. All right. Decide which is oxidized and which is reduced. Ooh, this is a little bit more challenging, isn't it? Manganese, it's a permanganate actually, with a -1 charge. Oxygen's -2, so your manganese has got to be a +7. The tin is a +2. H3O, which is a hydronium ion, +1 - 2. On the other side, we have manganese, which is a 2+, so it's going from a +7 to +2, so it's been reduced. The tin is gone from a 2 to a +4, so it has been oxidized. Tin 2 was oxidized. Manganese, the permanganate ion was reduced. And that makes permanganate the oxidizing agent and our tin 2 the reducing agent. Iron here is a +2. This iron is a +3. So iron is part of iron FeS, oxidized. Manganese, we already know in permanganate he's a +7. Over here he's a +2. So the permanganate was reduced. The oxidizing agent, therefore, is the permanganate. And the iron sulfate's the reducing agent. And time for a little stoichiometry. Hydrochloric acid plus aluminum hydroxide will give us aluminum chloride plus water. All right, we need to know the mass. We want to know what mass of hydrochloric acid in grams is required to react with 0.910 grams of aluminum hydroxide. So, first thing we have to do is change this to moles. 0.910 grams divided by the molar mass of aluminum hydroxide. Google, what's the molar mass of aluminum hydroxide? 78.00 grams in 1 mole. Okay, we're going from here to here. So my ratio is going to be 1 on the bottom, 3 on the top. So now we're at hydrochloric acid, and we need to know grams. So I need to change that back to grams. Chlorine is 35.45, hydrogen's 1, so times 36.45, and we should have business. 0.910 divided by 78 times 3 times 36.45. 0.226 grams of hydrochloric acid. Now the second part of this asks about how much water will be produced. So once again, starting with our aluminum hydroxide, 78 grams. This time our ratio is going to be 1, also 1 to 3. And we'll multiply by 18.02, which is the molar mass. So 0.910 divided by 78 times 3 times 18.02, 0.6307, 0.631 grams of water. So let's see what happens when we put those numbers in and if we're even close. We said that it was 0.226 and 0.631. 0.226, 0.631. Oh no. Well, I had 3 significant digits, so that should have been right. Let's see where I goofed. My hydrochloric acid was wrong. Should have had 1.28 grams. What did I do wrong, people? I must have hit something wrong in my calculations. I have it set up right. Divided by 78 times 3 times 36.4. Oops. That time I got 14. Oh, people, it's time for me to go to bed. Okay, so see, even I make mistakes. Number 34, methane burns in oxygen. What are the products of the reaction? CO2, and it's separated by a comma, H2O. Write the balanced equation. So what are we doing? CH. And that's going to be a gas, methane. And we're going to react it with oxygen. And that's going to be a gas. And we're going to make CO2. And that is going to be a gas. And H2O, and that will be a gas. Now, 1 carbon, 1 carbon, 4 hydrogens, 2 hydrogens, so we need a 2 out front. That gives us 4 hydrogens, 2 oxygens here, 2 oxygens here, so we need 2 out front of that guy. What mass of oxygen in grams is required for complete combustion of 38 grams of methane? All right. 38 grams of methane. Divided by the molar mass, 12, 13, 14, 15, 16 grams in 1 mole. My ratio, I have 1 mole of methane for every 2 moles of oxygen. And then oxygen has a molar mass of 32 grams per mole. So let's see if I can do this right this time. 38 divided by 16 times 2 divided by 32. 0.1979, we'll round that up to 0.198. I did something wrong again. Let's try it again. 38. 16 times 2 times 32. 152. Let's try that this time. There we go. What's the total mass of products expected? So we got to add up our carbon dioxide and our water that we're going to make. I'm going to hit pause, do the math. All right, to calculate our products, 38 grams of methane, going from methane to carbon dioxide, it's a 1-to-1 ratio. And the molar mass of carbon dioxide is 44 grams per mole. If we want to go from methane to our water, it's a 2-to-1 ratio. We would get 85.6. If we add those together, 85.6, 104.5, 85.6 plus 104.5, 190.1. Cross your fingers that I've done the math right. Ta-da! Yay!